Hey there, everybody. Welcome back. This is section 13.7 for Calculus 3. It's fall 2022 at College of the Sequoias. We are using the Anton Calculus Early Transcendentals book, 11th edition. 13.7 is on tangent planes with and the normal vectors. In chapter 13, we've been working on multivariable functions and partial derivatives. How does that show up in tangent planes with their normal vectors? Let's take a look. So we've got some surface S, and we've got a point P naught on that surface. We'll say the surface S is represented by some function of X, Y, and Z. And it'll represent a level surface at that point. So the surface is constant there. And that will equal D. Suppose C is a curve through P naught. So we've got some C or some curve going through the point on the surface, and we'll parameterize it using X of T, Y of T, and Z of T. So we got the line tangent to C at P naught is the R prime, because C, remember C, we're going to use R of T for our C's. So we've got our tangent line at that point is R prime of T naught. And since the curve is on C, we can plug in R of T into our function. X was X of T, Y is Y of T, Z is Z of T. We're still making equal to D, some level surface. So what happens? We'll take the time derivative of both sides. So ddt of both sides, the right side's a constant, it goes to 0. The left side becomes the gradient of f dotted with R prime of T naught. Okay, that's pretty cool. If the gradient of f is not 0, then the gradient of f is normal to the surface, because R prime of T naught is a tangent vector. And we know the tangent vector times the normal vector equals 0. Gradient of f must be our normal vector. And I didn't actually specify what curve we were using or what point we were using on that curve. So this must apply to any curve C that goes through P naught. So we can use that gradient of f to define the tangent plane at S, or for S at P naught. So our normal vector, oh, I have a lowercase n, that's just terrible. Get it together, Mr. Jones. We like to use big N for normal vector. Big N is the gradient of f evaluated at X naught, Y naught, Z naught. Since it didn't matter which curve, we had the same gradient. All good. This does require continuous first order partial derivatives at P naught. And of course, we do want the gradient of f to not equal 0. And so what does that give us in terms of some equations? We've got the tangent plane, or gradient of f dotted with R prime of T naught. These two are interchangeable. I think this one's easy to remember. And we could do normal line. So what's the normal line at this point? We're starting at X naught, Y naught, Z naught, and we're going in the direction of the gradient of f. So the normal line is T times that. This is pointing outward. That's it for the introduction. Let's just get to some examples in our next video. Peace.